Good afternoon, everyone. Lovely to see you all. My name is Chris Benton, and I'm doing a series of 5 talks on astronomy over the next 5 days between now and Auckland. So let's see what we've got. What you're seeing here is known as the Hubble Ultra Deep Field Image. And it was taken when NASA got its Hubble Space Telescope, and it pointed it towards a seamlessly featureless part of the night sky. And in particular, it focused on one tiny little spot, the size of a grain of sand held at arm's length. You imagine what a tiny, tiny spot on the sky that would be against a background of seamlessly featureless sky. And they held it there, and after about 11 days of total exposure time, that is what they saw. There are over 10,000 points of light in that image. Each of those points of light represent an entire galaxy. A galaxy being a collection of stars, usually billions of stars, in every single point, of which there are 10,000 there. Astronomers from there extrapolate that data, and from there they speculate in our observable universe, there's probably about 2 trillion galaxies. So you can't help but think and wonder, what's it all about and where are we in this big mix? That's why today's talk is titled, Our Place in the Universe. Where do we fit in? And this afternoon, we're going to go on a visual journey of discovery, starting with little humble Earth and you and I, and then we're going to move out through the solar system, the Milky Way galaxy, the local cluster, the Virgo supercluster, the Lanacare supercluster, right out to the extent of the observable universe. And then we'll speculate on the size of the entire universe. So buckle up, guys, we're going. Okay, so starting with Earth, our home planet. This was an image taken by one of the Apollo 17 astronauts in 1972. And one of the journalists asked the astronaut, what did we learn by going to the moon? And he quite wisely and profoundly said, we learnt about the Earth. We learnt how isolated, how fragile and vulnerable Earth is. It's one of the key things that we learnt by going to the moon. And he was very right. Just a little bit about us. We're a relatively small rocky planet. We're rocky in that we're not a big gas giant where life just can't form. You need solid surfaces for life, for the chemistry of life to get underway. So we're a rocky planet. We're small. We're 13,000 kilometres across. And I want you to remember some of the figures. You don't need to remember too hard about them because I'll be reminding you of them. But just be mindful of the figures that I present to you throughout this presentation. So we're 13,000 kilometres across. 70% of the surface of Earth is covered in liquid water, and that's what gives us this blue appearance from space. And of course, that is critical for carbon-based life. And from radiometric dating of meteorites from the outer solar system that come through our atmosphere that we gather up, dating them suggests the Earth is about 4.6 billion years old. So that's a little bit about Earth. Most likely the universe is thriving with life, but as far as we are aware of to this date, Earth is the only place where there is evidence for life. Scientists have identified over 2 million species of life, and they speculate there could be up to to up to 10 million species. So, yeah, they speculate there's over 2 million species. Fossil evidence suggests that life started on Earth relatively early, somewhere between 4.1 billion years ago. In other words, when the planet was only about 500 million years old. But it remained simple, single cellular life for over 3 billion years. And it was only about 650 million years ago that it developed into complex life, like plants and animals and the like. So admittedly, from a sample of n equals 1, Earth, our conclusion from there is life is pretty resilient. It can get started pretty early on a surface, as long as it's cooled down and there's some liquid water. It can get started early on. But complex life takes a long time to develop. It's a lot more involved. So how many are there? There's 8 billion of us Homo sapiens roaming the planet. I don't know how wise it is. I remember they were celebrating. The world leaders were toasting themselves with champagne when they reached the 7 billion mark. That was a few years ago. And I thought to myself, really, is that something we should be celebrating? They were, but we're now 8 billion of us. Just to give you a little bit of an idea of where we fit in, modern humans, Homo sapiens, we've been roaming the planet for about 200,000 years. Now, Earth, as I said, is about 4.6 billion years old. If you put that into an imaginary calendar, starting just after midnight on the 1st of January and finishing at midnight on the 31st of December. 200,000 years. Where do you think that fits in the calendar? Any takers for the month? Yeah, December. We came along on that calendar 24 minutes to midnight on the 31st of December. That's when we came along. For a big calendar, we came along right here. And, we think we're important and so on, and the way we quickly abuse the planet. So a little bit of some milestones of humanity. We've learnt to grow and culture crops for the last 10,000 years. We've learned to organise ourselves into collections with governance for the last 6,000 years. Industrial Revolution was about 250 years ago. And we've been sending rockets and people into space for about the last 70 years. Okay, so where does Earth fit in with models of the universe? The Greeks 2,000 years ago had already worked out that the Earth was round. Some people still haven't worked that one out, but anyway, I won't go there. But from their basic observations and their religious beliefs, they understandably thought that the Earth was the centre of the universe, and that the sun and the planets and all the stars went round the Earth, what they call the geocentric model of the universe. And it took till the mid-1500s when a Polish mathematician by the name of Nicholas Copernicus, you've probably all heard perhaps of his name in history, and he worked out that in actual fact the sun is at the centre of the universe, and the Earth and the planets go around the sun, and the stars are a very long distance away. And he explained it by saying, hey, it's just that we are rotating. That's what's going on. So it looks like the sun's going around us, but that is not so. And of course, that would have been considered heresy at the time. He literally released that paper on his deathbed. The day he died. He didn't dare release it before then. He would have been hung and quartered. Just putting Earth in perspective with the solar system. The solar system, is the sun, central star in the middle of the solar system, and then we have 8 planets from there. And you'll notice that we have here, we have 4 inner rocky planets, and there's the Earth sitting there, and then we have 4 large outer ice and gas giants. Now, you're probably wondering why the dichotomy of these small inner rocky planets and then 4 much larger ice and gas giants. My last talk, my fifth talk, is a journey through the solar system. We'll be addressing that and many other questions and commonly questions. We're going to explore the solar system in depth then. So for now, needless to say, here's the Earth. The Earth is 150 million kilometres, so there's 13,000 kilometres across. It's 150 million kilometres, so we're suddenly moving out to millions of kilometres now. Before the year 1781, before telescopes were used with some science for this, with the unaided eye, you can only see out as far as Jupiter. So you can see Saturn, they're in the sky, and Jupiter. We're doing a thing tonight, if the weather's good. It's 8:15, I think it is, upstairs. It's on my last slide. We're going to be doing some stargazing tonight. And if we're lucky for the clouds, you'll actually get to see Jupiter. Saturn would have just set. But needless to say, with the unaided eye, you can see out to Saturn. Saturn's about 1.5 billion kilometres. We're dealing in billions of kilometres now out from the sun, giving the solar system in those days an effective span of 3 billion kilometres. Then in 1781, this guy here, William Herschel, a British astronomer who built his own 48-inch telescope, and he identified Uranus, the next planet out. The solar system doubled in size overnight. It suddenly gave us the solar system a span of 6 billion kilometres. Then in 1846, this guy here, a German astronomer, Johann Galler, he identified Neptune, and suddenly the solar system span went out further again to a span of 9 billion kilometres. So we're getting out to some big numbers here, billions of kilometres. And then they also were aware that this small, rocky, icy objects called comets that are coming somewhere in the outer solar system, zipping around the sun and heading back out again. And it was this guy here, a Dutch astronomer by the name of Gerard Kuiper. And he postulated that there must be a reservoir, a collection further out of Neptune of lots and lots of small, rocky objects that are causing these comets. And he was very right. With the advent of coming online a new generation of large telescopes in the 1990s, and they were able to look further out into the solar system, and indeed they found this huge donut shape collection of millions of small rocky objects. This extended the solar system out to about 15 billion kilometres. They called it the Kuiper Belt after Gerard Kuiper. And they realized this is the source of what are called short-period comets. We all know what a comet is. It goes around the sun. You see them frequently. But what's a short-term? They're split into short-term and long-term comets. A short-term comet is a comet that the time it takes to go around the sun is less than 200 years. And a classical example is Halley's Comet. Probably all heard of Halley's Comet. We see that every 75 years. So that's a short duration comet, and that's where it comes from, that Kuiper Belt. Now, you might say, well, okay, how about long period comets? Yeah. So there was another Dutch astronomer by the name of Jan Oort who postulated there must be further reservoir out there. And with computer simulations these days, they're able to watch and track the trajectory of these comets that are taking longer than 200 years. Some of them take millions of years. And of course, the computer could go back and work out where they came from. This is generally accepted by astronomers. This is a computer sort of diagram analysis of this big spherical structure on the outer skirts of the solar system, where all these long duration comets are coming from. And you can see here, putting it in perspective, here's the solar system, here's the orbits of the planets and Neptune, here's the Kuiper Belt that goes out to 15 billion years. That entire diagram, boof, right in there. Look how big the solar system really is. That brings it out to a span of 20,000 billion kilometres. Obviously, the numbers are getting more and more ridiculous, and you just can't keep rolling out more zeros and numbers. So for that reason, astronomers introduced the idea of a light year. And that's a span of 2 light years. So what's a light year? A light year is the distance that light travels in a year. Light travels at 300,000 kilometers per second. Bat of your eyelid, 300,000 kilometers. Almost as fast as my cat runs to the food bowl when he hears the fridge door open. So that's about 7 times around the world. It goes in 1 second. So you might say, okay, that's 1 second. How about in a year? What is a light year? In a year, light travels 10 million kilometers. So that's a 1 with 12 zeros after it. That's 1 light year. So the sphere is thought to go out from the sun about a light year each way. So the solar system's now recognised to have a span of about 2 light years. I'm not in your way, sir, am I? No, that's all good. So there's the solar system. Just a little bit of brief about the sun. We'll go over it a bit more on our last talk. But the sun is a star. And the bottom line is, it's all about the sun. Over 99% of the material or the matter in the solar system is all in the sun. The planets, here's a to-scale diagram up there on the left-hand side. And you probably see our little wee Earth there, say in comparison with Saturn and Jupiter, it's a tiny, relatively tiny planet. But there's the sun next to it. So 99% of all the material is in the sun. Volume-wise, you could fit the Earth into the sun 1.3 million times. The Earth fits into the sun. And someone asked once, can you get stars if the sun's a star, these planets? Do all stars have planets around them? And I replied to that by saying, have you ever tried baking a cake without spilling crumbs on the bench? Someone says, you haven't seen me bake cakes. So, but needless to say, it's all about making the sun, and the planets are just crumbs on the bench from making the star. That's a general principle of stars and planets. Okay, so our sun, as I mentioned, it is a star, it's an average star. Because of gravity, huge pressures and temperatures build up in the centre, and it's caused about 15 million degrees in the centre. And because of that, it fuses hydrogen. So hydrogen molecules get rammed together to form helium. And that, long story, but that process releases energy. 600 million tons of hydrogen gets consumed and burnt up every second in the sun. Seems like it's okay. The sun's going to be around. You don't need to rush to the bar to have one last drink in case it runs out. It's okay. There's loads and loads of hydrogen in the sun. It's estimated the sun's going to live about another 5 billion years. Don't know about us though, but anyway. That 1 second of energy is 1 million times humanity's annual energy consumption. That's per second. But of course it's spreading out in all directions and gets filtered down, coming to us and through the atmosphere and so on. And as human beings, we're pretty good at wasting stuff. Okay, now, so that's the solar system. It's 2 light years across. The sun in our solar system, in turn, is just one star of 450 billion stars in our Milky Way galaxy. So a galaxy's synonymous, or analogous, if you will, like a city. It's a gravitationally bound collection of stars and other astronomical objects. And if the galaxy was a city, stars would be like buildings and suburbs and so on. So it's disc-shaped. Often if I'm doing a talk, after dinner talk or something like that, I might pick up a dinner plate and say, this is the Milky Way galaxy. It looks like a dinner plate, if you will. And we're out here in the suburbs and we're looking, so I pick up the dinner plate and I said, look, we're here, we're looking through the dinner plate towards the centre. And this is a photograph. You've probably seen many of sort of amateur photographers taking these, even with their iPhones these days. And we're out here and we're looking through the disk towards its centre. And that's the shape and our perspective of the Milky Way. So we're only one of 400 billion stars in the Milky Way. Now, span-wise, So from here to here, our Milky Way, remember we were blown away when we said the solar system was 2 light years in size. Our Milky Way in span is 100,000 light years. Remember, 1 light year is 10 million kilometres. We've got 100,000 of them across. We sit out here, out in the suburbs. We're about halfway along the disk. We're about 26,000 light years from the centre of the galaxy. That's where we sit. This here, by the way, is an image of the Andromeda galaxy. It's our nearest spiral galaxy, or disc-shaped galaxy, if you will. We can't take a picture of our own galaxy from outside. It's like someone saying to you, can you take a picture of your house from inside your bedroom? You can't do it. You can take a picture of the neighbour's house, but not your own. And this is Andromeda galaxy, which we'll talk a little bit about shortly. So, yeah, that's what we would look like. So we're sitting out here, but we're now up to 100,000 light years. Pretty mind-blowing, isn't it, the size of our galaxy? Up until 1924, it was generally considered that our Milky Way galaxy was it. That was the entire universe. We've solved it, guys. We know what it's all about. But there was little fuzzy spots in the night sky. The telescopes weren't powerful enough to resolve them any further. So they called them nebula, and accordingly to what constellation in the sky they were looking at, such as the Andromeda Nebula. It was a funny little bit. The word nebula in Latin means mist. Gorillas in the nebula. Here's a movie. So it wasn't until 1924 that this guy here, Edwin Hubble, yes, Hubble Space Telescope fame, and he had the biggest telescope at the time, the 100-inch telescope, and he was able to resolve the stars in this fuzzy nebula, misty-looking nebula in the Andromeda. And this is one of his original plates, photographic plates that he used, of the stars that he could resolve. And you'll see here, he's labelled 3 stars with an N beside them, because N stood for nova, or new star. He went back through his previous plates and realised where those 3 dots are, those stars, they weren't there on previous plates. Oh, they're nova, so he put an N beside them. Then he went back and looked at some further plates, and he realised that this one here actually had been visible on previous plates, but it was on some and not with others, and it was a different brightness. So he concluded it was what they call a variable star, and you can really see he's crossed the N out and put VAR exclamation mark. He realised he was dealing with a variable star. Now, I know astronomers get excited very readily, but why was he so excited about that? Because this lady here, Henrietta Leavitt, earlier on, had made the discovery that a type of variable star called Cepheid variables pulsate. She identified that the rate of pulsation of that star was exactly correlates with how bright that star is. Its intrinsic or absolute brightness, not how bright it looks from our perspective, but actually genuinely how bright that star is. So they're known as Cepheid variables, and that's called Leavitt's law now. So he got excited by that. So he made note of how its pulsation rate, he could tell from there how bright it actually was. And there's a very simple formula. If you know how bright something is at a distance, you can see how bright it is from here. It's apparent brightness. It's a very simple formula, just working out the distance to something. So he worked out from there that nebula, that misty patch in the sky, is 800,000 light years away from the Milky Way. And that was pretty obvious to everyone then that that was an entire galaxy. These little misty nebula, if you like, were all just what we call island universes. They called them at the time. We now call them galaxies, and it's totally separate. And that was due to Edwin Hubble, who did that. Modern calculations tell us that it's actually 2.5 million light years away from a lot more. His calculations were out a little bit, but he solved that. His point was totally correct. Now, you thought the Milky Way was big at 100,000 kilometres across. We've moved on from that now. The Milky Way is just one of about 80 galaxies gravitationally bound together in a group called the local group. And that's called a galaxy cluster. And it's called the local group, is what we call our cluster. And yeah, you're now looking at a diameter from here to here is now 10 million light years. You're not dealing in thousands of light years anymore. You're dealing with 10 million light years. There's 3 main galaxies in it, big spiral galaxies. The Milky Way here, the Andromeda Galaxy, which you saw the picture of earlier on, and it's 2.5 million light years away. And then there's a smaller one, the Triangular Galaxy. And the other ones are small, sort of what are called dwarf or irregular galaxies. So there's 80 in total. I put here the Andromeda Galaxy and the Milky Way Galaxy are planning to, it looks like they're probably going to merge in about 5 billion years' time. So people often use the word collision. They're not just going to come together like that. They're going to just sort of go past each other and do a little bit of a dance and a bit of a swipe and just gently merge. So that's going to happen in about 5 billion years' time. But wait, there's more. So that local group cluster of galaxies, in turn, is one of about 100 clusters forming what we call the Virgo supercluster. So we're dealing in superclusters now. We've gone through solar system, galaxies, galaxy clusters. We're now dealing with superclusters. Superclusters aren't defined by being gravitationally bound. They are bound, you're probably aware, you may have heard that the universe is expanding. There's an unknown force that's been called dark energy that's driving the universe apart, making it expand. And because of that, galaxies are all moving apart from one another on large scales. And the way galaxies move together, that's how they group superclusters. So the Virgo supercluster is a group of clusters of galaxies that all seem to be moving together due to the expansion of space. We thought we were big at 10 million light years across for the local group. We're now dealing 110 million kilometers across for this Virgo supercluster. 110 million light years. I ain't finished with you guys yet. The Virgo cluster since has been found to just be a branch of a much larger supercluster called the Lana-Care supercluster. And that's 520 million light years across. Now that's 500 million light years across the Lana-Care supercluster. Huge. Then, talking on scales of billions of light years, those superclusters then form sheets, have observed to form sheets and thread-like filaments that wrap themselves around large regions called voids that are very sparsely, they just have a very small number of galaxies in them, and that's it. And those voids can be up to anything up to between 30 and 300 million light years across. They make up most of the volume of the galaxy, these voids. But you can see it here, these sheets. This is a diagram. I'll show you some real data in a minute. But these are a diagram here, how it forms sheets and filaments that wrap around these voids. And it's called the cosmic web, because it looks like soap suds or a spider web, doesn't it? So they call it the cosmic web is what they call it. Okay, now what I will mention in here is dark energy, because people often want to know a little bit about dark energy. It is only observed in the middle of those voids. It's a weak energy. Gravity is a lot stronger, so we don't feel it on the scale of the solar system or the Milky Way galaxy, even within the clusters and so on. It's only felt in those voids. And as I mentioned, they can be up to 300 million light years across. Okay, so how do they know all of this? Most of the original groundwork was done by this. It's called the Sloan Digital Sky Survey Telescope. It's a diameter 2.5 meters, so it's a good size. It's a wide-angle telescope with its lens, so it's ideally suited for doing surveys. And the idea behind it is night after night after night, it just constantly scans the night sky, documenting and recording very precisely the exact position and the exact distance to all the galaxies. And from there, it's able to build up a 3-dimensional picture of the universe. This is real data from the Sloan Digital Sky Survey. You can see it there. You can see all these sheets and filaments. So these are all galaxy clusters and superclusters forming these sheets. There's filaments going on here, and they're all wrapped around these voids to form the cosmic web. Got a little movie for you to see so you can help to visualize that. So we're going to go through a 3D journey through it. So this is all from real data. It's not just something made up by an artist. It only takes less than a minute. But you can see here we've got a nice supercluster here. Looks like a big sheet. We're now going through a void, a few satellites, a few galaxies. Every point of light you see is a galaxy. You can see here, you see like a little void that's been wrapped around. Nice little sheets and filaments there. There's a filament. So you can see what I mean. We're going through a void now. Here we go. There's some more sheets and filaments that we're going past. But you can see it's the cosmic web. And each one of those dots of light is an entire galaxy consisting of billions of stars. And each of those stars will have planetary systems. So there you go. So tonight over dinner, someone says, "What did you do this afternoon?" You can say, "Oh, I flew through the universe." Why? What did you do? There you go. You've been through the universe. Isn't that amazing? Okay. So the next question, you think, okay, I'm aware of the size of structures and how structures are organized. How big is this observable universe? And the answer is easy. It's the distance light has traveled to us since the beginning of the universe. But of course, that begs the question, well, how old is the universe? Once again, here's our friend again, Edwin Hubble from the Hubble telescope in 1924, proved that Milky Way was just one of many galaxies. So the idea was to try and determine the age of the galaxy. In 1929, he made the observation that galaxies appear to be all traveling away from us, receding. But he also noted the more the distance the galaxy was, the faster it was going from us. And there's only one conclusion from that. It means the universe is expanding. So how fast? So he was able to plot this graph here on the horizontal axis, distance from us, and on the vertical axis, the velocity, or how fast they're traveling away from us. And that's what he was plotted there. So you can see the closer they are, the lower the velocity, the further the distance, the higher the velocity. And he was able to draw a nice straight line, a direct correlation there. It's just a mathematical thing. When you get that, the slope of the line is the rate of acceleration. So he was able to work it out from there, the rate of acceleration, so you just count backwards and calculate the age. Like in those early days, he was a little bit out, but today the general measurement is considered, the universe is about 13.8 billion years old. There's three very important points of evidence that point to that. One is the fact that you can see everything's traveling away from us. Two is what we call the abundance of elements in the universe. They went through the theory, and they're starting here with they've been nicknamed the Big Bang. By the way, the Big Bang, it's a myth that people think the Big Bang means how the universe formed. The Big Bang says nothing about how the universe was formed. That's a whole different field of science. The Big Bang just purely states that the universe was once small and hot, and it's expanded and cooled down since then. That is the Big Bang. So in the early conditions, it was extremely hot, and then stars developed, and through that whole process, they calculated out, if that model is correct, we should see an exact relative abundance of elements across the universe, and the theory matches the observations perfectly. Another bit of evidence. Now, the third bit of evidence that really is the most important is that in these early times of the universe, it was just so hot and dense that atoms couldn't form, just electrons and protons flying around and light zipping around, and it was opaque. And when the universe was about 380,000 years old, finally it was big and cool enough where protons and electrons could join to form neutral hydrogen, and suddenly it became transparent. Light could travel across the universe. The universe became transparent. And high energy light would have been emitted at that time, which would have permeated throughout the whole universe as the universe continued to expand. And the cosmologists worked out, well, if that was so, our whole universe should be permeated with that light, but it has been stretched out to microwave wavelengths, which is just between infrared and radio waves, just long, harmless wavelengths of light that your TV, for example, picks up. We should be permeated by it. No one could find it. And then in 1964, there's a couple of guys here, Penzas and Wilson, were doing some experiments with microwave wavelengths, with telescopes and so on, for purposes of communication. And they found this constant static they couldn't get rid of, and they thought maybe it was pigeons doing poop in their device. They cleaned it all out, and suddenly it dawned upon them they had discovered that permeation of microwaves go throughout the universe, because they matched it up. I wanted to have a serious look at this, work out what temperature it is and the properties of it, and there it was, 2.7 degrees Kelvin, exactly what the cosmologists had predicted. There it was. Remember your old analog TVs, and they're all going fuzzy between channels? That's the cosmic microwave background. That's the original light from early on in the universe, when the universe first became transparent. So that's what it all looks like today. I'm not going to talk, I could talk for an hour on that, which I'm sure you don't want to hear, but that little speckled represents little fluctuations in temperature and concentration of matter in the early universe. There's a powerful lot of information that can be extracted from there. The only reason I've put that up there is that reflects they can work out the overall geometry of the universe from that. That's relevant coming up. So how big is the universe? Let's split it up. The observable universe is the light how far light has travelled since the universe began. We now know the age of the universe. We know it's a bit about its geometry as well. You might say, well, if the universe is 13.8 billion years old, it's easy. It's 13.8 billion light years across. No. The universe, of course, has been busy expanding because of dark energy. And it's calculated that we observe light about 46.5 billion years in each direction. So the diameter of the observable universe, how far we can see out, is 93 billion light years. Remember, 1 light year is 10 million kilometers. 23 billion light years across. Okay, so how about the entire universe? So that's as far as we can see. Surely there's universe after that. Yes, there is. How big it is, we can only speculate, but let's look at that. So the cosmic microwave background that I showed you briefly shows the observable universe appears to be flat. So the entire universe is one of 3 geometries. It's either flat, and goes on forever, infinite. It's either got an open curvature and infinite and goes all directions, or it's closed, like a sphere, if you will, curved but closed, with an finite, but with a patch of it where our observable universe still looks flat. And there's a law in geometry that says if you get a sphere, it must be at least 250 times the size of any given region that appears to be flat. And it's like the Earth, we're down here really low, so like on the sea, it appears to be flat, but we know it's not. But just gives that appearance if you get a small enough region on the surface of a sphere. So it must be at least 250 times the observable universe. So the universe may be infinite, but the smallest size it could possibly be is 23,000 billion light years across. You feeling important? So, let's just say it's extremely large. Let's go home. And I'm sure you all are very important. I'm sure about that, no doubt whatsoever. But just keep this in mind. We all are one of 8 billion human beings. Human beings are one of 2 million identified species on Earth. Earth is one of 8 planets in the solar system. It's about 13,000 kilometers across. The solar system is about 2 light years across. The sun, our solar system in turn, is just one of about 400 billion stars. Each of them will have planetary systems, most likely. The Milky Way in turn is 100,000 light years across. It is only one galaxy in about 2 trillion galaxies. The observable universe is 93 billion light years across. And the entire universe is at least 250 times that size. And that's our place in the universe. Thank you. Now I'm happy to